SwayamPrabha. Digital India. Educated India.
So welcome back to day 11 of our course, which will be the second last day of the course. And we are actually now in diffusion, right? So last lecture we have analyzed the first real tracer volume diffusion data and also derived the equation why we plot, for example, the volume self-diffusion, because tracer diffusion is about equal to self-diffusion as a function. So the composition concentration, we call it radioactive activity, as a function of depth squared when we do the sectioning. And then these profiles can then be evaluated. We got this. So basically what we see here again is what we saw in the last lecture. So we see we plot the obtained diffusivities for the Cantor system. And for this is the 5-component cobalt, chromium, iron, manganese, nickel alloy. And importantly, we measured these diffusivities for all constituents, all 5 components, in comparison to this quaternary alloy, which doesn't have manganese. Also there, all the 4-component self-diffusivities were measured for volume self-diffusion. And they are compared here now for with different matrices. Matrices meaning alloys, or in one case, pure metal, nickel. All of them are FCC. And you can see what we basically concluded last time. First of all, a comparison is more meaningful if it is done in this Arrhenius representation as a function of the inverse homologous temperature, not so much in terms of the absolute temperature, because of the different melting temperatures of these matrices. You can also see that depending on how you plot it, whether you take the absolute or the homologous temperature as a reference, you will see that the course or the data for the self-diffusion, volume diffusion coefficients are either rather on the fast side or rather on the slow side compared to the others, right? So if we do a comparison on the homologous temperature, which is the correct comparison, then this is the diffusivity data we are looking at, and it is rather slower. But here it is rather faster as compared to these other materials. Now we have to again analyze what do we see here. And we see when we look at the span at constant temperature of the diffusivities which we measure, then they vary by about 1 order of magnitude at max, going from a pure element, self-diffusion. We always look at nickel diffusivities here, and then going to binaries, ternaries, quaternaries, up to the equimolar 5-component alloy. Then a variation at constant homologous temperature, or also even at constant temperature, by 1 order of magnitude is not unexpected, because of the fact that you have disordered FCC lattice contributions. So whenever you add a new constituent, there is bound to be lattice distortion. There is bound to be different ways the elements interact with the vacancies. Here we always have substitutional diffusion mechanisms working, so vacancies are important. And these vacancy binding interactions to specific elements are different. And this is probably also the reason why there are some differences going, especially in the activation enthalpy, going from 4-component cobalt, chromium, iron, nickel to 5-component cobalt, chromium, iron, nickel, manganese, because the manganese is the most different of these atoms. And most probably what we see here in terms of differences of the diffusivity between these two alloys is an outcome of adding a new element, manganese, into the system. Not so much that there is a new element and you change the configurational entropy, but that it's the specific choice of manganese and its interaction with the other binding partners, but also affecting how the other pairwise interactions, let's say between cobalt and chromium, is affected by adding or not adding manganese. So this is like a very complex process affecting the whole alloy structure and all the interactions. We normally take only binary interactions into account because it's more simple and because we think the ternary quaternary interactions are leveling off more quickly than binary interactions, but still there could be an effect. This is also a little bit to be seen here when we now think of how do we describe diffusivity, right? So it's an activated process. So it has this prefactor times exponential dependence. This is why we use the Arrhenius representation to look at activation enthalpy. Now, it's important that we can put a little bit more physics into the description. These not can be taken as an empirical parameter to describe the results. But in terms of diffusion theory, it's consisting of different terms: a geometry factor, a correlation factor, a lattice parameter itself, and the attempt frequency. Attempt frequency means how often does an atom need to try to do the diffusive jump before it's getting successful. Lattice parameter is clear. And then the geometry factor is basically related to the geometry of the lattice, whether it is strongly anisotropic or isotropic, and it's normally in these cubic systems around 1. The correlation factor itself is different because it's basically correlating how large are the probabilities for jump from a given atom at its site to the neighboring site, and how large is the probability for the atom jumping back or jumping elsewhere. So in order to make a real diffusive excursion, it needs to not jump back all the time, but it needs to jump to different places also to basically span the configurational space. Theoretically, normally, because it's also related to the lattice geometry as well as the interactions between the different atoms and also between the vacancies at the different atoms. So this is a term from which you can estimate the vacancy interaction or the vacancy binding enthalpy of the different species. In experiment, it's difficult. Basically, what you do is you do these experiments as we have done. And for a given alloy system, all these parameters stay constant except the diffusion entropy. So you determine the diffusion entropy from the experimental results, then you have that. And then you can basically compare different alloys and lattices in order to get the correlation factors, or at least the ratio of correlation factors. What we see here is again a comparison of diffusion entropy and activation energy for diffusion, self-diffusion in the volume, for these different matrices, always referring to nickel as the diffusing element. And there you can see that basically you have a more strong difference in the behavior for the 4-component system, but not for the 5-component system, right? So that again hints that the high configurational entropy of high entropy alloys is not decisive for the diffusion, and it's really the addition of which element you pick in order to make the alloy and not how many. This is much more important to ask the question, which element did I alloy and how are the binary interactions with this additional element to all other element constituents, and how also does the addition of this new element change the binary interactions of all the other pairs? And this is obviously a complex task. This very low diffusion entropy, which is seen for this 4-component, almost Cantor alloy, is unusual. So it suggests that there is some kind of change in lattice stiffness or in ordering locally. You can have a short-range order in a disordered solid solution, meaning that preferential sites in the FCC lattice are occupied only by 1 or 2 of the 5 species, right? Many people are searching for experimental proof of a short-range ordering because it would be thermodynamically expected. So far, nobody has been successful. This is only just an indication. We cannot prove anything with that. But when you look at it, and this is now kind of representation of the so-called Meyer-Neldel rule. Do you know the Meyer-Neldel rule? It's very important in material science because it says there is a correlation in any thermally activated process between prefactor and activation energy. So the term before the exponent and the leading term in the exponential. And you can see here, again, for various alloys, including high entropy systems, that they all fall very nicely on this line which is indicated, which is the Meyer-Neldel rule, which says there is a linear correlation between the delta S, the term in the exponent, and the Q, which is in the exponent, and the delta S, which is in the prefactor. And so it means that, especially for the high entropy system, this is very nicely fulfilled. But it also means, and this is important, that when you go from pure systems to high entropy systems, this plot shows you that there is no change in the atomistic process of the diffusion. So it's all by the same mechanism.
Does this rule stand only for the linear relationships?
Yes, the Meyer-Neldel rule predicts that there is a linear relationship. So
So it might not be true for any quadratic or any.
yeah, I mean, so far we see very small numbers of indications that there is a deviation, because the Meyer-Neldel rule just says that these two things are correlated, right? In a linear way. And in the abundant fraction of activated processes, this is true from experimental data, right? And maybe I write down the name here. So it's not a law, but it's empirical correlation derived from experiments. We also saw that there was a crossover temperature in volume tracer diffusion. Basically, you can now ask, why is this coming about? Why is the manganese addition causing a difference in this crossover temperature for the temperature dependence of constituent diffusivities which are not manganese? And this might actually be related, when you look at it, at how either the activation energy or the average mixing enthalpy changes when you add manganese to the 4-component almost Cantor, so going from medium entropy to high entropy systems. And basically, it just tells you that there are opposing effects of manganese addition. That tells you, again, it's very important which component do you add. So it's not the number, right? And the manganese addition might really be specific because it might change the vacancy interaction of other elements. You know, basically, it's like you add a thief into a big group, and now the thief carries and takes away some of the vacancies and keeps them. So all the other people cannot have easy access to the vacancies because the thief has taken them all. Not all, but some fraction. And this is the picture which is coming from here. So nickel shows the lowest diffusion rate in both, irrespective whether it's a medium or high entropy alloy. The activation energy can be correlated with more negative enthalpy of mixing, average enthalpy of mixing in the Cantor alloy, again, because of the manganese addition. And also the crossover temperature, where cobalt diffusion at higher temperatures is faster in Cantor alloy, can be due to opposing effects, more negative average entropy of mixing of the nickel and the decrease of the melting temperature of the quaternary alloy, again because of manganese addition. And as a general outcome of this, we can say diffusion in high entropy systems is not per se sluggish. You have to watch how you do the comparison between different alloys. In the literature, it has been done mostly on the absolute temperature scale. The homologous temperature scale is the right one. In any case, however you compare them, the differences are small and are within the expected range if you go from one alloy to another one. Going to single crystals, back we saw the first results beginning with this chapter on volume diffusion in high entropy systems. This shows you basically the single crystal which we experimentally had, which was basically obtained in Poland with a collaboration partner, where they are specialized in growing single crystals. And you see that there is a common orientation and no chemical heterogeneity on the scale of SEM. EDS measurements. And if we now look in this slightly complex plot, again, Arrhenius representation on a homologous temperature scale, showing you the constituent self-diffusivities in polycrystalline and in single crystalline simples. Again, for the 4-component medium Cantor and for the 5-component high entropy Cantor. And basically, what you see that the polycrystalline data and the single crystalline data do align very well, which means we have correctly evaluated our polycrystalline data in terms of the volume diffusion. Grain boundary diffusion was occurring, it's always there, but it is was correctly taken into account so that the analysis of the data was done in the correct way. It also shows you, the same results as obtained for the polycrystalline material. So I think this was basically showing, yes, the data were correct and nobody can argue against our conclusions, because even for single crystals data, this has been shown. So this is, I think, summary of the volume diffusion in these two alloys. There is specific interactions. I'm not going to read through all of them because I said them. But a take-home message, the variations are not large. They are within the expected regime if you go from rather normal alloy, binary, or even pure metal to 5-component high entropy system. What matters is if you add a strange element to your alloy that changes the most of the alloy properties. Manganese, in this case, is the most different one, and this is why we see in detail strong differences, but overall the picture is diffusion is just as it should be. It is not regarded to be sluggish. But we always see, when we think of this effect of a very specific component addition, that we basically still have to worry, do we do the right comparison, right? Because we now have compared chemically dissimilar systems with manganese, without manganese, binary system, 5-component system. And because these binary interactions matter so much, we should have a better comparison. So this is why we go now to a comparison where always we have 5 components, given 5 components in the system, but we vary the composition from dilute solid solution to equimolar high entropy alloy. And ask the question, is there a discontinuous transition from solid solution to high entropy behavior? And this means that when we think of the earlier lecture on how to display phase equilibria, we use this very handy isopleth. So it means here we go basically from pure nickel to the equimolar Cantor alloy, and which would be here. And basically stay at some temperature always in a solid solution, disordered solid solution FCC range. Right? And that means we can always compare in a maybe more meaningful manner, because we always have all the binary, same identical binary interactions in our system. You ask, is there at any composition the appearance of a high entropy effect? So is there a concentration limit which distinguishes between dilute solid solution, conventional solid solution, and high entropy system? And people have found that when they, for example, plotted the lattice parameter as a function of nickel concentration going along the same isopleth section, that around about 60 atomic percent nickel, there is a deviation from Vegard's law occurring. Do you know Vegard's law? Vegard's law is basically a rule of mixture for the lattice parameters. So it means that the lattice parameter variation for normally a binary dilute solution should vary as the concentration varies. Now, would you think this is a good law describing the behavior of concentrated alloys? No. It is expected that it deviates because it's not a law. This is why I put it in parentheses. It's just a limiting description, basically looking at the thermodynamics of solutions and asking how does the solution develop when you go to the dilute limit. So it's going in the opposite direction, not to the high entropy case, but to the dilute limit. And people have also seen and compared then for all these different alloys which are shown here, the hardness of the values. And again, they found that for about 60 atomic percent nickel, there is a deviation from, again, a constitutive law, which is not a law, but which is an approximation for dilute solutions, complete solutions. And again, for me, it has to be expected that there is some kind of deviation at the higher concentrations, right? So it doesn't mean this is an indication of a high entropy effect. And people were discussing this in different ways. What we did then was to take all the alloys, or not all the alloys spanning the range from pure nickel to Cantor. And you see, except the pure nickel, always we have the 5 constituents in the system. Sometimes really in dilute solutions. So in this case, each of them has only 2 atomic percent. And obviously for the Cantor alloy, this is like 20 atomic percent each. And obviously we have to now, for each of the alloy we investigate, look at the microstructure, look at the melting temperatures, which is shown here again, in order to do the diffusion experiment, or analyze the diffusion experiments in the correct way. People have also investigated for the same material selection, always diffusion couples. And one is shown here. So they put pure nickel against the Cantor alloy, and you see that the interface is about here. And then they measured nano indentation to get mechanical measurements done in the interdiffusion zone, because the fusion couple is put together. Then you let them interdiffuse. You make sure there is no phase transformation, so it's just mixing on FCC lattice. And then you can basically screen your hardness data. And if you, again, compare this to what I've shown you earlier, cell parameter, so deviation from Vegar's law, you see it's about at the same composition, where you can say there is a deviation in the behavior of the hardness values. So this is at least going along with what has been published in comparison to this one here, the Labouche model. So it means this confirms that there is some kind of change at about 60 atomic percent. But this could have different reasons. It could maybe change the local ordering of the material at different concentrations. It could also be that some vacancy binding mechanism is different. It might be that the splitting distance of dislocation because of stacking fault energy is changed, which would affect the mechanical properties in a major way. So it could have many causes, and one of them would be that the material undergoes kind of a phenomenological transition from normal to high entropy system. And actually, maybe going quickly through this, it's also seen that for the high entropy system, the stability changes quite strongly. So here as a function of temperature left or 1/, temperature right, you see left grain size and right basically stress. And what you can see is that always the high entropy system shows that you can go up to the highest temperature before grain growth sets in or before the material loses its high strength. Obviously, both of this is related, right? So if you have smaller grain size, then you have higher strength because dislocation interaction with the grain boundaries, and at some point dislocation nucleation becomes difficult. So Hall patch relationship. This is actually an important point because the retention of defects here in high entropy alloys is larger. And this, I think, is one of the unexplained but very important effects of high entropy systems. You can see that somehow, and I guess, this is really a guess, because of the high entropy, because of the lattice distortions, that we have a reduced mobility of the defects, a stronger interaction, maybe easier formation of sessile defects, logs we have discussed, so that the material can keep the defect content up to higher temperature for longer times. And this makes the material obviously keep a small grain size up to higher temperature and also keep high strength up to higher temperatures. It does, again, not mean that the high entropy system has something to do with diffusion. If we now look again at the volume tracer diffusion data as a function again of 1/, homologous temperature, and we now compare these different systems going from dilute solid solution to high entropy system. The symbols represent the different alloys. So here again, we have only 2 atomic percent for each constituent. So this is the dilute solid solution. And we have the high entropy system, and we have this 60 atomic percent nickel in between, where all these measurements showed some kind of change in behavior. And we basically have these symbols for the diffusion of the respective alloys. We have then as the dashed line diffusion in this Cantor system, and solid is the comparison of diffusion in pure nickel. Because there we have full temperature dependencies, which we do not have for all the alloys in between. And on a homologous scale, tracer diffusion coefficient in these high entropy systems are 1 to 2 orders of magnitude smaller as compared to a dilute solid solution. But again, this is the same, or is a similar picture as we got from changing really constituents, adding manganese or not, right? It's this 1 to 2 orders of magnitude difference. In this case, the difference in alloying behavior is even stronger because we really have dilute solution, while previously we comparing a 4-component concentrated alloy to a 5-component concentrated alloy. And so both comparisons show the same indication. No exceptional behavior concerning diffusivities, no sluggish diffusion. This is also nicely shown here. When we, again, as a function of the nickel concentration, look at both the volume diffusion coefficients as well as the melting temperatures, the red data. So you see melting temperature varies when we go from pure nickel to Cantor alloy. And we see also that the diffusion data for the different species varies differently with this composition, right? So some show that first the diffusivity goes up when you alloy, when you add dilute solutes into your material and then go down. Some show first a decrease and then a slight increase. Overall, there is no discontinuity at 60 atomic percent nickel. So in terms of diffusion, 60 atomic percent is showing similar behavior as the other compositions. Could you guess why you could get these opposing effects at low concentration? So you have pure nickel and you add now 2% cobalt, 2% iron, 2% chromium, and 2% manganese. Some of the diffusivities, yes, formation enthalpy, especially affecting the vacancy binding energy, yes. And this can give you opposing effects because some of the elements profit and some of the elements do not profit. And so it means they get disparate behavior initially, but then basically when you keep adding more and more solute, then you level out, then it's getting more like an effective interaction behavior. And so that it doesn't matter so much anymore how the different constituents interact with vacancies. So, yes. So the opposing effect, sophisticated competition for vacancies between the different alloying elements. When we now look at theoretical calculations, we need to go maybe a step below CalFat, because now we have to look at detailed interactions. And this was done by the group of Professor Carsten Albe at Technical University of Darmstadt in Germany, who was having this Darmstadt, yes. He was basically we had a joint project on this, and we worked together. So we were doing experimental, and they simulated basically the similar thing in using atomistic simulations. And they basically use mean field interatomic potential, because for the 5-component systems you cannot get really a detailed potential, and use the typical LAMMPS software package in order to calculate molecular dynamics. The important point which they added here is that they used kinetic Monte Carlo, KMC, calculations where they basically took into account that in a disordered alloy which has many constituents, that each atomic jump would have its individual barrier, because it depends on whether this specific atom, let it be nickel, has manganese as a neighbor or cobalt as a neighbor. And this was really taken into account here for the first time.
Modified version of the Monte Carlo simulation.
Yes, it's further advancement, because normally you take an effective value for all of these atoms. And what they basically can look at, which we cannot do in detail in experiment, is look at, for example, vacancy concentrations as a function of the different alloy constituents. So they also went along the isopleth section, right? Pure nickel to Cantor. And these numbers here for the differently colored data is for the different alloy concentrations. And you see, when you look at the vacancy concentration for all these alloys, or also as a function of just the amount of nickel, basically it's constant. There are small variations, but they might also come from specific setup or so. Sorry. This is now the kinetic Monte Carlo simulation. And so normally in the random alloy model, which everybody used before, they would basically have an effective barrier. But here they basically take this individual barriers into account. So it's like you have, whether you have a red atom or a blue atom, you have a different barrier for the jump. This gives a more consistent description, because each species now has a distribution of migration barriers. What they basically were able to calculate is shown here. And this is remarkable, because normally diffusion is a process that is very difficult to simulate. Because for taking the detailed atomic interactions into account, what you need to do is to take all the individual steps, and not only one jump, but on a femtosecond time scale, calculate the behavior of the material. You need to have sufficiently large simulation boxes, otherwise you will not get the interactions right. And you need to simulate over sufficiently long times, so that you really have diffusion and not only mean square atomic displacement. They were able to do that, and you see here a comparison between the tracer diffusivities obtained in experiment, red, and in this kinetic Monte Carlo simulations, blue. And I would say it's fantastic. You see there are differences, but if there wouldn't be differences, this would not be real data. So you have to expect it. But you see the trend is right, the activation barriers are roughly similar. So this is very good data. Looking at the concentration dependence, we also again have red experiment, blue simulation, and we see when we do all these comparisons, vacancy migration, entropy on nickel tracer diffusivity, we have quite a good agreement on the order of magnitude scale. Sometimes different concentration dependence, so you see here they go down first when you go from pure nickel to dilute solution, but the experimental data was showing first a small increase. This is probably because vacancies are very difficult to really integrate into any type of atomistic simulation in a realistic way. But I would say the outcome is mutually consolidating what we knew. And they basically confirm each other in terms that there is no change going from dilute solid solution to high entropy system, which is outside of the expected range you expect. There is no change in vacancy concentration. There is no real change in macroscopic diffusivity. There is no discontinuity. This is maybe very important. So it means volume diffusion is unaffected. This is, I think, now confirmed. Now, what about grain boundary diffusivity? Could it be affected while volume diffusion is not affected? Well, yes, right? I mean, in the end, it's two different diffusion processes. And if the grain boundary structure in a high entropy system would be different as compared to the grain boundary structure of the dilute solid solution, then there could be differences. It could also be that due to a strange effect of the high entropy alloy design, the grain boundary properties could be affected in such a way that you would get wrong diffusivities for the volume. So we need to check both in order to be able to know, is there a change or is there not a change? And this is why we basically obviously need to measure grain boundary tracer diffusion. Again, in single phase solid solution higher entropy alloys, so again Cantor alloy. But now we have to dive a little bit deeper into the basic description of diffusion, because for grain boundary diffusion it is getting more complex as for the volume diffusion description. So we take the Fisher model, which is the accepted model for grain boundary diffusion description. What you see here is a representation of a single grain boundary. It has a certain width delta, otherwise it's extended in 2 dimensions. And if the tracer is applied on this plane, then obviously if you allow it to diffuse in, it would certainly go into the volume. But let's say we keep now conditions, low temperatures, short times, that volume diffusion doesn't play a role, but grain boundary diffusion still can proceed, then it would diffuse along the grain boundary plane, and you would probably get a diffusion concentration profile as the outline here. You know, it's high at the boundary, at the plane where you applied the tracer, and then it's decaying according to some exponential dependency. But if we now go to do this experiment at intermediate temperatures, there is always also out diffusion from the grain boundary plane into the both adjacent crystals, right? And this is taken into account in the Fisher model. And basically, we have to then take into account 2 diffusion fluxes. One along the grain boundary plane. Plane means slab of thickness delta. And the second out diffusion into the single crystalline half volumes. Obviously, they take place along according to different diffusion coefficients. Along the grain boundary, it's the grain boundary diffusion coefficient. Into the volume, it's the volume diffusion coefficient, which we have determined already. So this is basically how it looks like if you use a top view. Right, so you have diffusion fluxes and you have concentration profiles coming from this, according to this description. Now, we have to basically describe mathematically how this works. So we take the grain boundary diffusion as well as the out diffusion with volume diffusion coefficient into account. So we write fixed second equation, but one with the grain boundary diffusion coefficient within the boundary, and the out diffusion with the volume diffusion coefficient for these x values which are beyond the thickness of the grain boundary. Well, we take now the concentration, the diffusion fluxes, so basically continuity equation into account. And this gives us these conditions listed down here. Like mass conservation plays a role here, right? And so we basically then can very good. So we have y here in this direction, right? And we would have z or c, then x here, right? Why do you think z is not given?
In this model, I can say that because composition looks like fixed, like no concentration.
This is the grain boundary plane. And this is the plane where I applied the tracer. So what matters is diffusion along the boundary. This will be the same here, as here, because I applied tracer everywhere, right? So it means we linearize the problem because the diffusion flux along the boundary is only going along the boundary. And this or this doesn't matter, right? And this helps us to simplify.
But along the green boundary, like this direction is not same. Like always, why will change?
No.
Green boundary has some different.
Grain boundary is like this in this model.
It's not always like equal distance. Like diffusion will have to be. Like,
No. If you apply the same concentration here, then the same concentration will be here, will be here, will be here. This is the approximation of the model, right? So you have like a given plane, and then diffusion is going along this plane. If you would have differences, then this is not described by this pure boundary, but then you would have some obstacles locally in the boundary. But for this Fisher model, which describes the boundary as this homogeneous slab of material with thickness delta, then in this Z position or in this Z position, you would have the same concentration profile as a function of distance to the original plane. Yeah? But because of this linearization only in one direction, y, we can simplify and apply Taylor expansion to basically get the simplification for these two versions of second law of Fick. And then with a lot of math in between, people have solved these equations with the given boundary conditions, continuity equations, for constant source and for instantaneous source, so thick film and thin film solution. This is not very useful for experiments because it contains parameters that we cannot easily determine. Then an approximative solution, which is a very good approximation of the exact solution, has been developed. We can also use the exact equations, and this is what we normally check, whether in our specific conditions the solution, the approximative solution can be mapped and corresponds to the exact solution. But we do this only for one condition or so, because it's too much work. And then if we are satisfied, then we use the results of the... They are mathematical parameters, and not all of them have really physical meaning. No, they are in there, but basically adapted in a way that they can be related to how you measure diffusion in a sectioning method. No, it's not a... Yeah, it's... Let me show you. You know, in these solutions, you get then only values which you can really determine, which are varying, like grain boundary thickness, volume, and grain boundary diffusion coefficient, time, and so on. But for example, something like this numerical value, this comes out of mapping the approximate solution onto the exact solution, and then this has no physical meaning, right? It's just a numerical fit parameter. Yeah. And this is then basically the approximate solution which was done by Leclerc, which is specifically adapted to sectioning measurements. So meaning that when you plot the layer concentration, C bar, again, it's a bar because it's the average over the entire layer. And you plot it logarithmically as a function of the penetration depth to the power of n. Then this gives you access directly to the diffusion coefficient. And so this is then the approximate mathematical description. If you now apply the boundary conditions correctly, then you get a function which can be mapped onto the exact solutions if n equals 6/5. 6/5 why? No reason. This is a mathematical fit procedure which worked so far very well. But this is why we also have to go for a solution using the exact solutions to check if also in the particular case you are just investigating, this n equals 6/5 is fulfilled. There is no physical reason. So far it has always worked in a very good way. Yeah, and then you can get for constant source or for instantaneous source different solutions, obviously, because the boundary conditions are different. And you see you get these so-called Leclerc parameters. And these you have to check for your experimental conditions, and they will determine which of the solutions you can use. For the constant source, they must just be in the range beta larger than 10, alpha larger than 1, and then you can use the approximate solution by Leclerc in order to describe grain boundary diffusion. And only the grain boundary diffusion part is described here, right? If you have an instantaneous source, then you have to be more careful because there are 3 different regimes for the beta parameter, which basically give you different mathematical fit functions for what we call here the double or triple product. P double triple product is this value. Right, and you see here, this double product is just the product of grain boundary width and grain boundary diffusion coefficient. Normally, when you are describing an alloy which also shows segregation, then you need to use the triple product. This is then segregation factor times grain boundary width times grain boundary diffusion coefficient. So that means you have to take into account that in general there are these 3 regimes, A, B, and C type. And obviously this is most important for the B type, because in the C type you can basically assume there is no volume diffusion. Here you get an effective volume diffusivity out of the measurement, and this is the important regime. Which you can get out, right? This is how it looks like. So if we now look at cobalt self-diffusion in cobalt, and you now choose 2 different temperatures, one which is low, one which is higher, then you see the differences, right? In the low temperatures, you only have one slope of your data when scaled over the penetration depth squared, because this is the solution for pure grain boundary diffusion. In the B-type kinetics, you have two contributions. You have volume diffusion and grain boundary diffusion. And if you want to analyze the grain boundary diffusivity, then you plot it as a function of penetration depth over with the exponent 6/5, 1.2. And then it will be linear in these coordinates. Obviously, the volume diffusivity doesn't follow the same kinetics, right? Because it has a different solution of the Fick equation. And so it's not linear. So you can get both diffusion coefficients from the single measurements, but you have to plot them on different y scales. And this is basically summarizing what I just said. Instantaneous and constant source have different ranges of values, and then these related parameters which go into this general description here given below are then varying differently. So this is just summary if you want to really use and apply this. If you look at the literature, it's getting a little bit even more complex, because there also exist transition regimes going from pure C grain boundary diffusion to pure B type case to pure A type case. So it's meaning you are at temperatures and times where you have kind of a set of Leclerc parameters which are not really giving you a way of deciding how to do which solution you should use, and then these values and the profile shapes are indicated. But this is really for specialists use only. So summarizing what we should know about grain boundary diffusion. There's always a range where volume diffusion is dominant, then you determine an effective diffusion coefficient as in type A, and then you measure the volume diffusivity. For low temperatures, you can directly measure grain boundary diffusion coefficient, and in the middle region, either very long times or not so low and not so high temperatures, you have to check really very carefully what conditions you apply and how to solve the diffusivity. It's actually the most complex, but also the most valuable regime, this B-type regime, because in one measurement you measure grain boundary as well as volume diffusivity, and you can also use it to determine grain boundary thickness. Yeah, because what you measure is the triple product. So if you know the segregation factor and you measure the diffusivity, you can infer this delta, the grain boundary width, from it. And we have done this for several different materials, also for high entropy systems. And what we get is roughly 0.5 nanometers. There are some deviations, but this is in oxides, so you would expect it to show differences. But for all transition metals, it's 0.5 nanometer is a very good description. If you know the grain boundary thickness, you can also determine the segregation factor, right? And this can be very useful because otherwise it's very difficult to get this value in a quantitative form. Any microscopy has difficulties because grain boundaries are too thin. And atom probe tomography along boundaries is something very difficult because of rupture of the sample. So let's go to see the results of grain boundary tracer diffusion. Again, we go back to our 4-component and 5-component alloy. We basically look at concentrations and whether we have grain boundary segregation or not. For this, we use focused ion beam to cut thin lamella and do TEM investigations, or we use this same method to produce these sharp tips here, and then do atom probe tomography. what you basically can see is that especially for the Cantor alloy very nicely here, see there is no segregation at the boundaries. So we know segregation factor is 1. That's fine, right? Because we can also directly measure grain boundary thickness from our grain boundary diffusion data. And this is then showing you data at 2 different temperatures, one low, type C, one higher, type B kinetic regimes. Again, direct grain boundary diffusion, and then both bulk and grain boundary diffusion contributions to the profiles. We get the triple product and the double product shown, and basically we see again for the different constituents, all the constituents of the high entropy alloy, differences are not so big. When we again compare grain boundary diffusion, in this case with the other FCC matrices where we have analyzed it, we again see also grain boundary diffusion doesn't vary much. And for example, if you look at this one here, you see that showing much more sluggish behavior than the high entropy system. If we look at temperature dependence, then again, when we compare 4 and 5 component systems, we see there is a crossover, but otherwise there is nothing which would indicate that a high entropy effect is there. And again, we have to think here of the manganese addition, which might change the game more considerably than going from 4 to 5 components. So it means it's nice that we have no grain boundary segregation. We can directly measure the width of our concentration profile. Cantor alloy shows lower grain boundary diffusivity only below 800 Kelvin, so only in a certain range of temperatures, right? Here. At higher temperature, the tendency is reversed, so it means the high entropy alloy has the more sluggish diffusion behavior along the grain boundaries in some temperature range, but in the other one it's more anti-sluggish, also, no, right? And this seems again to be affected mostly by melting temperature change as well as the change of the average binding enthalpy or mixing enthalpy, especially for the nickel when you add manganese. And just adding one additional element doesn't change much or nothing at all. Now we also have special grain boundaries, not special in terms of the definition by the CSL theory, where you have special symmetric positions. I have talked about this in one of the earlier lectures. But when you now process a material, let's say you cast the material, you want to roll it out to get a sheet. Then you think of it, you have to do quite a large change of shape, right? And also if you, for example, go to a steel factory, you cast 30 tons of steel in one go, and it directly comes out as a slab. What do you mean? How thick is that slab when it first comes out of the first processing step? So typically for the sheet metal which you buy, which has a thickness like of this guy in the end, how thick is the starting?
20 to 40 mm.
More, 30 or 40 centimeters.
40 centimeters.
This big. And then it goes, and when it comes out, it's this big or thinner. So it means it's rolling deformed, and it's basically compressed to minimize pore sizes, which always are there, pores after casting, in a huge way. And this is not only for steel, any casting material will undergo these processes. So there is a severe deformation involved in most of the products which are metallic, which are alloys, which we use. And now you can ask the question, I think you should ask the question as material scientists, how do the structures inside of the grains, the defects, and also the grain boundaries change because of this processing? And there has been a suggestion by Russian colleagues on so-called non-equilibrium grain boundaries. So the picture is you just have grain boundaries and they have a higher excess energy density because of the defect accumulation during deformation at the grain boundary. So far, when you look at the textbook, it's described as you have a dislocation in your crystal, it goes to the grain boundary, whoops, it's gone. Infinite sink. You can put as many grain boundaries and it doesn't change anything. Well, that might not be true because it's a structural entity. It changes the grain boundary structure. And they have developed as a model, and it means that when many dislocations, lattice dislocations, go to the boundary, the grain boundary will be transformed into something they call non-equilibrium grain boundary. So, these are boundaries associated with additional defects. The name I don't like, non-equilibrium grain boundaries, because any grain boundary would be a non-equilibrium defect if you basically anneal the material at high enough temperature for sufficiently long time, right? So the grain boundary would vanish. The single crystal is the equilibrium structure. So I'm talking here about conditional equilibrium again. So as long as the grain boundaries are there, the non-equilibrium state has the higher excess free enthalpy as compared to the grain boundary structure, which has the same overall misorientation of the grains, but the grain boundary structure itself would be relaxed. So this is the equilibrium structure to compare to. And these grain boundaries should feature excess grain boundary energy as well as long-range elastic strain fields. And excess grain boundary energy corresponds to faster diffusion along the grain boundaries. There's a so-called Borisov model. Which relates the excess energy density increase of a boundary with increase in grain boundary diffusivity. And so if we look at materials which have been severely deformed, and we just look at, for example, the grain boundary diffusivity of nickel in these different materials, all of them were severely deformed, as indicated. Then just for the grain boundary diffusion part, we still see two branches. So there is no volume diffusion shown here. So all these measurements were done in pure C-type regime. So we have different types of grain boundaries. Some have a higher and some have a lower grain boundary diffusion coefficient. And so in terms of comparing them to volume diffusion, the slow ones are actually what we normally find as the fast diffusion pathways along the grain boundary network. And the fast ones we should then call ultra fast because they are even much faster. And this is the picture you have. You have like a grain boundary network, and then some fraction forms a super network with a larger mesh size. And these boundaries then are affected by the deformation in such a way that they probably have accumulated more dislocations and formed these grain boundaries which have ultra fast diffusivity. Excuse me.
What are the major changes?
Yeah, I mean, the diffusivity changes, the grain boundary structure changes.
In terms of diffusion, what are the major changes in terms of diffusion after deformation?
I show you here. Yeah, this is the change. This is the normal grain boundary diffusion. along relaxed grain boundaries, and this is for the non-equilibrium grain boundaries. If you now compare it, you compare it at constant temperature, right? So you compare maybe here, then you see, whoops, almost 4 orders of magnitude difference. If you extrapolate to lower temperature, it might be 5 or 6 orders of magnitude. So this is a huge change in grain boundary diffusivity. Actually, it's so huge that the mechanism needs to change in order to explain it. If we now look just for one material, again nickel, and compare it, grain boundary diffusion coefficient as a function of 1 over the temperature. Here, just the temperature is good because it's always nickel, so we don't need the homologous temperature. It would be the same. And we basically compare now undeformed pure nickel of high purity, the blue data, undeformed nickel of less purity, we see this difference. Why is that? This applies for any alloy you have. If you look at higher purity material, then you see that the grain boundary diffusivity will be larger. What reason could there be? Yes, impurities segregating to the grain boundaries. So this is a segregation effect.
It's a pure material.
He's saying the nickel is pure. How are they?
Well, this is pure 5-9er. So it's 99.999. And this is 3 9er and an 8. So this is 99.98. And the difference is mostly in the light elements, carbon, nitrogen, and so on. They like to segregate at the boundaries. Segregation means you decrease the grain boundary excess energy, otherwise segregation wouldn't happen. But that means that diffusion along these boundaries is more difficult because these atoms block some of the spaces which rather were open without them. Right? When we now deform the dirty nickel, with 3 9er 8, and then look at the diffusion, we get 2 branches. One is actually showing us same behavior, same diffusivity as the much purer nickel. This is because now, after deformation, the grain size is smaller, so the given amount of impurity is distributed over a larger total grain boundary area. So you can purify a material by making it fine-grained. And we have this ultra-fast contribution. And this is an interesting thing because we see it for all severely deformed materials. And we can then apply this Borisov model, basically getting the excess grain boundary energy out of the ratio of the 2 diffusivities, grain boundary diffusivity and volume diffusivity. And this means that we have roughly an increase of 30% of these ultra-fast boundaries which show the ultra-fast diffusion, which is a huge value, but it's not unphysically, it's a reasonable increase. And we see that we can also get the second branch, but this is not important for here. And as I said, this is a general trend for all kinds of materials, different crystallography, different melting temperatures, and they show the same thing, which means it's really a generic behavior of severely deformed, strongly deformed material that you have this effect, and you should take this into account. This will affect precipitation behavior, this will affect any kinetics in your system. And when you look for it, you can even use bright field TEM, which is much easier than anything else. And once you see a contrast at some of the boundaries looking like this, which I call serrated contrast, And this is a good indication that you have some of these non-equilibrium boundaries present in your system. If you go to higher temperature, they will anneal out. You get rid of the serrated contrast at the grain boundaries. You will not see the fast contribution to grain boundary diffusion. And if you do high resolution and map strain fields on the atomic scale, you will see that these boundaries have larger width, and they have a very strong decoration with residual lattice dislocation debris, so partial dislocations, full lattice dislocations, giving you a huge strain field of the material. Now, this was just the introduction about what I want to tell concerning additively manufactured high entropy systems. Again, Cantor, a high entropy alloy, because FCC is easier, because this has been established. This is how the microstructure looks like after additive manufacturing of the materials which we have been investigating. They were done from powders which were ultra pure. They were done in South Korea. And what you see is the typical structure, right? So you see basically in the microstructure the impact of the previous scanning of the laser. This is laser bed powder fusion, which was used here. And otherwise you see very, very strong anisotropic microstructure as you would expect it for additive manufacture. You also see that there is dislocation network, and quite strongly. So when you look at this bright field image, you see there's a lot of this grayish contrast. These lines and these curls looks like a cat has played with the wool your mom used to knit socks. These are dislocation networks. So it means huge number density of dislocations after additive manufacturing because of the very fast cooling and the heat flow which goes in not very defined directions, because the laser scanning on top of the layer and top of the layer and next adjacent layer will also affect how the heat flows away. This also leads to segregation, and you see here very nicely that we have this strong manganese segregation after additive manufacturing. This is anti-segregation, causing anti-segregation of iron, so manganese is going to the boundary and iron is depleted there. So this is a completely different microstructure as compared to polycrystalline high entropy alloy, same composition after arc melting and homogenization, and this needs to be taken into account. What we do measure is a diffusion rate, which is again huge. So here you see the value at this particular temperature measured for the grain boundary diffusion coefficient of additively manufactured Cantor high entropy alloy. And this is actually in the same range so it means, this is why this title of this part of the lecture came about. In terms of their diffusion coefficients, these boundaries, grain boundaries after additive manufacturing, show similar diffusion behavior as some fraction, about a third of all the random high angle grain boundaries in severely deformed material. So they show this unusual non-equilibrium grain boundary behavior. This favors precipitate formation. Additionally, they also have a different segregation behavior, showing more segregation at their boundaries. So phase stability in additively manufactured materials is bound to be very different as compared to the same material in terms of its nominal composition, but produced by a conventional route, like doing some kind of liquid processing, homogenization treatment, maybe deformation swaging, and then again relaxation treatment. And again, you see here it's also following similar trends, right? So you have, like at the low temperatures, a branch where you have this very, very strongly different diffusion behavior in these non-equilibrium grain boundaries, then you have something like a transition regime where the boundaries start to relax. They go maybe to transient states, which also have a lifetime, and in the end they fall on the grain boundary diffusion coefficient values, which are also true for the relaxed random high angle grain boundaries. And so this is, I think, shown here for the first time for a high entropy system, but it's should be taken into account beyond high entropy systems. So when you do additive manufacturing, it is very likely that because of the non-equilibrium processing conditions, you end up having a material also having these non-equilibrium properties and microstructures. This is related to defect densities. This is then related also to all kinds of things like segregation, like also local structures affected by these huge defect densities. So in the design of a material or in the post-processing after additive manufacturing, one really should think about how to either avoid it or get rid of them, or maybe you even want these features to have in your material. So it's a kind of design knob, a new tuning fork you can use by either using it for your advantage or knowing it's there and then taking it out afterwards. Many of the results, so again, when you, for example, compare also additive manufacturing, not of the high entropy system, but of pure titanium or of titanium 6-4 with conventionally prepared materials, and then you look at self-diffusion values along the grain boundaries of a substitutional or of an interstitial diffuser, you can again find out what is really the underlying mechanism for these grain boundaries to allow these faster diffusion rates in substitutional diffusion. And then it's inferred from the comparison between these two that it's really an excess free volume in the boundaries which causes the grain boundary diffusion coefficient to be larger. So it's somehow a distribution of excess volume, probably because vacancies and dislocations find grain boundaries as a sink. And both of them, for both of them, a grain boundary doesn't have infinite depth as a sink. So there is a lot of dislocations and vacancies you can store in a grain boundary, but the grain boundary structure will be affected. And apparently it serves to make these non-equilibrium grain boundaries. And it doesn't matter if you have a thermal pathway or if you have a mechanical deformation pathway. Thank you.